All right, this is part 2 of electromagnetic radiation. So far we've talked about the divisions of the electromagnetic spectrum, talked about the wavelength. Well, you'll notice down here we have another term. So here was the wavelength. We have something called the frequency. So let's start out by defining that. Frequency is defined as the number of waves that pass a given point in 1 second. So we could think of our unit here, and this is a little bit incorrect, so come to physics and we'll clean it up, as waves per second. It's actually called cycles per second, but we could say it as waves per second. But scientists didn't like this, so they said, let's rename it. Let's call this a hertz, H-E-R-T-Z. You'll notice here it says HTZ. Well, if you were on a lake, or a symbol, let's get that down real quick. Symbol is a lowercase letter f. So if you were on a lake and it was a nice warm summer day and you were bobbing up and down about every 5 seconds or so, that would be a pretty low frequency. And let's say a storm rolled in and all of a sudden the waves picked up and you're bobbing up and down about every second. So the frequency went up, the frequency with which the waves pass. You'll notice that we have here, you have to be careful with the terminology here. So here we have 10 to the 21st, 10 to the 21st positive. Here I have 10 to the 6th, and it looks like this number is a lot bigger, but let's be careful. So let's look at this. So we've got a super, super small wavelength here. These waves are cycling so fast, their frequency has got to be astronomically high. So this says shorter, but I think it's easier to put this in terms of numerical. So it's got a smaller number. This is a larger number. So 10 to the 21st is much larger than 10 to the minus 13. So look at the relationship between wavelength and frequency. Well, let's look at the other end. If these were our waves, it would take, it says lower. So I think a better word here to put is in terms of the value of their frequency, it's going to be smaller. You're going to have fewer waves that are going to pass in a second, and so you have a smaller value. Well, if you look at 10 to the 2nd and 10 to the 6th, it looks like this is larger. So you have to look at this as a trend. 10 to the 21st to the 6th is the range, minus 13 to the 2nd is the range. So if you look at it as a range, what you can see is that wavelength and frequency are also inversely proportional. We can represent this. So if we multiply wavelength times frequency together, we get a constant, C. And it's not just any constant. This constant is this, we call it the speed of light, and it really should be the speed of electromagnetic radiation. So it's a little confusing. It's a little bit misleading. It makes you think we're just talking about visible light, but it's all light. And the constant is 3 times 10 to the 8th meters per second. So our symbol for speed here is C, and the value is 3 times 10 to the 8th meters per second in a vacuum. If you send light through another substance like glass, it actually bends the light and we get something a little bit different. So we can use this equation. This equation is valuable to us. So we have C equals F lambda. Now, notice we said that frequency and wavelength are inversely proportional, and that matches up with what we've got going on. So if we hold this constant, if we have variables on the same side of the equation, variables on the same side of an equation are always inversely proportional. This is going to show up on your physics pretest. So if you come to physics, I'm going to ask you about this. We're going to have lots of formulas. Now, in this case, this is constant, but if this wasn't constant, if this could change, what we would see is that frequency, if I held this constant, these two would be directly proportional. If I held this constant, these two would be directly proportional. So if variables are on opposite sides of the equation, they're considered directly proportional. All right, well, let's run a sample problem. How can I use this mathematically? If I have a wavelength of 0.658 meters, I could ask, what is F? What is my frequency? Well, I have a constant here, so it would be 0.658 F equals 3 times 10 to the 8th. And when I solve for F, I'm going to have, this is a, well, let me pause it here. I'm going to get that my frequency is 4.6 times 10 to the 8th. If I wrote this, hertz, HZ. If I wrote this in scientific notation, this would be 6.5 times 10 to the minus 1. So if this is a small number, that needs to be a larger number. Makes sense. But what if I asked you, let's do one more sample problem before we wrap this up. Let's say I have, one of the questions I might give you is, let's do green light. Let's do microwave. Let's do red light. And let's do UV light. So if I said put these in order of energy, highest to lowest. Could you do that? Okay, take a crack at it. Pause the video if you need to. All right, I'm just going to number them. And it's pretty easy to do now because I have my diagram here. But what I would see is that I've got UV light is the only one that's up towards this end. So this is going to have the highest energy. And that makes sense. That's what can give you an actual sunburn. So I know microwave is way down here. So this is going to be number 4. So then I have, what about green light and red light? Well, you have to know the spectrum. So as I go from UV, let's come up this way, radio, microwave, infrared. Then I've got Roy G. Biv. So you need to know Roy G. Biv. So my UV light's going to be the highest energy. Green is going to be higher than red. So green is going to be number 2. Red is going to be number 3. And my microwave will be number 4. That's another type of problem, another example of a problem that we might ask you over electromagnetic, the electromagnetic spectrum. All right, that gets us where we need to go for kind of understanding the basics. We will practice this in class. That's all for now. Thanks for watching. Have a good day.